Now what we've been doing so far is differentiating explicitly. But how about we do implicit differentiation? Implicit differentiation, it is our very familiar chain rule, rates of change, it's all the same idea. So here's y equals x squared. As I mentioned to you before, what we're really doing is we're solving an equation here, and we're saying I'm going to do the same thing to both sides of the equation. In this case, I'm going to differentiate both sides with respect to x. Now on the right hand side, the x squared I can differentiate explicitly. I can do that with respect to x. The left hand side I cannot. I can't differentiate y explicitly with respect to x. They are different pronumerals. So what we are really doing is say, well, no, but I can do it explicitly with respect to y. That I can do. But in order to balance the left-hand side up, to make it the same thing, I need to multiply by dy dx. And you could think of it like a fraction. The dy's are cancelling, and you still get d dx. Differentiate y with respect to y, you get 1, and so there we have our derivative. Dy dx equals 2x. Now, of course, we don't put that sort of setting down, but that is what we're really doing. So now if I've got something like this, x equals y squared, I don't necessarily have to make y the subject, because what I can do is differentiate implicitly. So on the left hand side, sure, I can differentiate that with respect to x, not a problem. On the right hand side, I can't. So on the right hand side, I'm going to say, no, I'm going to differentiate it with respect to y, and then multiply that by dy dx, and then it'll balance it out. So I'll end up with this. 1 is equal to 2y dy dx. Now I make dy dx the subject, and I have the derivative. Okay, it's in terms of y, not in terms of x, but it is the derivative. If you wanted it in terms of x, then I would just substitute in, well, in this case, it would be y equals x to the power of a half, I would substitute in. But see, the problem is, think of the graph. Let's draw it up. It's our sideways parabola. It actually is more useful to substitute in the y value for this, for the rate of change. If I substitute in the x value, let's say it's here at x equals 2, then I've got two possible answers, because our problem is that x equals y squared is not a function. And so the derivative, depending on which part of the curve I'm looking at, I've got a positive slope or I've got a negative slope. Well, which one? I don't know. But if it's this particular point up here that I want, well, if I substitute in the y value, then I get this exact one that I want. So actually, for this one, it's more useful to substitute in the y value than the x value. If I had to differentiate this, x squared y cubed, well, I've got two things multiplied together. I've got to use the product rule here, because remember, y is actually a function of x. So I do have two functions of x multiplied together. So I'll write down the first, x squared. Differentiate the second, y cubed. But hang on, I can't differentiate y cubed explicitly with respect to x. So I'll do it implicitly. I'll differentiate it with respect to y, 3y squared, and then multiply that by dy dx. Plus, write down the second, y cubed, differentiate the first. Well, that's not a problem. I could do x squared with respect to x. I get 2x. And I would end up with this sort of expression for my derivative. 3x squared y squared, dy dx plus 2x y cubed. So if I want to find the equation of tangent to this circle at the point 1, 2, root 2, at that specific point, well, to find the slope of the tangent, I need the gradient function or the derivative. I don't need to make y the subject. I can just differentiate this straight away. All I'm going to do is differentiate both sides of this equation with respect to x. X squared, not a problem. I can do that explicitly. 2x. Y squared. Okay, I'm going to have to do that implicitly. I'll differentiate it with respect to y, 2y, multiply that by dy dx. And then on the right hand side, differentiate 9, I get 0. Make dy dx the subject, and I get minus x over y. So for this derivative, I need both the x and the y value. And if you think about the circle, well, there's one over here, that makes sense. Because if I just substituted in an x value, again, I've got two possibilities. If I just substitute in the y value, I've got two possibilities. But if I substitute in both the x and the y value, then I get the specific one that I want. 1, 2, root 2, substituting in both the x and the y value, I get minus 1 on 2 root 2, so there's the slope that I need. Point slope formula, play around with it, and there it is in general form. X plus 2 root 2y minus 9 equals 0. So being able to differentiate implicitly is a very powerful thing. It allows us to differentiate things like this a lot quicker. I've photocopied in our notes there out of the old Cambridge book.